We are going to start now the next lecture, lecture 4 of chapter 2, class 11th mathematics, relations and functions. So in this chapter, we will discuss the graphical representation of functions and some examples of the real functions. So the first definition we have, it is the graph of the function y is equal to fx. So we have already seen that x belongs to some x set A, and we have a function defined from a to b. Then we are saying f of x, we are saying that is equal to y, that is y is the element of this b, and a x is the element of this a. Then the points we obtain from this, that is x comma y, which are satisfying this fx is equal to y, or we are writing it is x comma fx. These points, these are the coordinates we are saying. The collection of these coordinates, it constitutes a graph. So we are saying the graph of a function fx is basically the collection x comma fx or x comma y, where y is equal to fx. Now if we plot these points on the coordinate plane, we are talking about, we have taken, this is the x-axis, this is the y-axis, these points we have drawn on the x-axis, these points we draw on the y-axis. And suppose we have drawn all these points and we obtain some curve, say it is in this form, this is shown over here. It is a curve y is equal to x cube we are talking about, and we are obtaining the curve in this form. So what we know from the definition of the function is that corresponding to each point of the domain, there is a unique image. It means if I draw a line parallel to the y-axis, if I draw the line parallel to y-axis, anywhere we are drawing this line, then it should not cut the graph of this function. This is the graph of this function. It should not cut the graph of this function at more than one point. So this is called the vertical line test for f to be a function. So we are having two conditions. First is that we should, this graph we are talking about, it should be defined for all values of a. X belongs to a, we are talking about, it should be defined for all values of a. And second condition we have is that if we draw a line parallel to y-axis, this line we are talking about, at any point we are drawing this line, then it should not intersect this graph at more than one point. So if in place of this, suppose the graph we are drawing, I am talking now about this second figure, this figure we are talking about, this is the function. We are saying x square by a square plus y square by b square is equal to 1. This is equation of an ellipse. So we are saying the graph of this function will be like this. If you plot these points, you substitute the different values of x, you will obtain different values of y, and you plot these points. Then what we are saying is that if we draw a line parallel to y-axis over here, suppose I am talking about this line, it is intersecting this graph at these 2 points. So what our vertical line test says is that this is not a function. This is not a function. So this is the vertical line test for checking whether the f is a function or not. So I am again repeating the procedure. The first thing we have to do is we are writing y is equal to fx. We are plotting the points x, y. These are called the these points we are saying we are drawing the graph of the function. Graph is the collection of all these points x, y. Then we draw a line parallel to the y-axis. We are not just drawing one line. We are saying if we draw any line parallel to the y-axis, then what we are saying is that it should not intersect this graph. This is the graph of the function. It should not intersect the graph of the function at more than one point. And second thing we will have is that for all x belongs to a, this line that we have drawn over here, it should intersect at some point with the given graph. So both the conditions, that the function has for every element of the domain, it has a unique image that will be satisfied. Next, we have the definition of an algebraic function. So a function f is called algebraic if it can be constructed using an algebraic operation starting with polynomials. So this term polynomials is used over here, and we have given the definition of this term polynomials. So we are saying a function y is equal to fx, which is of the form a naught is equal to x raised to the power n plus a1 x raised to power n minus 1 plus so on up to an, where a naught, a1, an are real constants and n is a non-negative integer, then this fx is called a polynomial function. We have already studied px. This thing we have studied in terms of px. We are saying px is a polynomial if a naught x raised to the power n plus a1 x raised to power n minus 1, it has this form, so on up to an. A naught is not equal to 0, then the degree of this polynomial, it is n. Then we are saying any function y is equal to fx of this form. We are writing, you can write y is equal to px, or we are, in this case, we are writing y is equal to fx. So this is a polynomial function. Now next we have given some graphs of the polynomial function. Some examples are given over here. So the first polynomial function we are talking about, it is a linear polynomial x y is equal to x plus 1. So if we draw the graph of this function, we are saying this is the x-axis, this is the y-axis, and this is the straight line we are talking about. If we plot this line y is equal to x plus 1, you know how we plot these points. We are putting x is equal to 1, we get y is equal to 2. We put x is equal to 2, we get y is equal to 3. So coordinates of points we have, it is 1, 2, 2, 3, like this. We plot these points over here. This is 1, 2 point. The next point we have plotted, it is 2, 3. We have joined these points and we obtain this graph. Now if we look at this graph over here, one thing is clear, that for every value of x we can obtain a value of y. It means domain of this function, it is R. Why real number? Because we are saying for every x belongs to R, we have a value of y. Second thing we are talking about is, if we draw any line parallel to y-axis over here, it will intersect this graph at only one point. So this is a function, this is a polynomial function, this is a function we have proved. And now we have to calculate the range of this function. So range of this function, we are looking at this graph, we are saying this is an infinite line over here. So what are the values of y it can obtain? So it can obtain the values of y from minus infinity to infinity. So it is important to mention over here that we have already studied the intervals of the real line or the real numbers. Now we should know that if we are talking about the real numbers, we are talking about all the real numbers, it can be represented as minus infinity to infinity. It is important to note over here that this minus infinity and infinity, these are not real numbers. These are just the symbols. These are not real numbers. One thing is, these are not real numbers. These are just the symbols. There are extended real number. There are another kind of number that are called extended real number. These are basically the extended real number. We are not interested in those numbers right now. But for us, these are just the symbols for infinity and minus infinity. And an important thing to note over here is that as these are not real numbers, so we are not going to close these brackets over here. We are not going to write it like this. We cannot close the brackets over here because we are dealing with the real numbers, and these two numbers, these are not the real numbers. So whenever we are writing minus infinity to infinity with open brackets, it means we are talking about all real numbers. We are talking about all real numbers. Similarly, suppose I am talking about a comma infinity. It is closed at a, open at infinity. This thing is fixed, that whenever we are writing infinity or minus infinity, this interval is always open in your case. Now what this thing means, if we have to represent these numbers on the number line, we are saying there is a number a over here, this number is included, so we are putting the dark dot over here, and we are saying all the numbers greater than this. This represents that x is greater than equal to a. This is this interval. If suppose we are writing minus infinity to b, both sides it is open, so we are saying there is a number b over here, it is open from this side, and we are talking about all the numbers which are less than b. So this is x is less than b. These are all the numbers in this form. So these kind of intervals, these are also the intervals we are talking about, or in place of intervals we generally call these as rays. In place of intervals we call them as rays. So we have different kind of rays with over here, a comma infinity, it may be closed, open a comma infinity, we have minus infinity comma b with open bracket, then it is minus infinity comma b with closed bracket, and it is minus infinity comma infinity and open from both these sides. So I am again repeating over here that wherever we are writing minus infinity or infinity, this bracket should be open bracket, because this interval cannot be closed, because this infinity is not a real number. So the range we are saying over here, we are saying it is y belongs to R. So we can write that the range set it is minus infinity to infinity. Next we have the polynomial function y is equal to x square. So when we draw this function, we are saying this is x-axis, this is y-axis. If we plot this function, this is the graph of this function, y is equal to x square. So the domain of this function, what values of x you can substitute over here. We are talking about domain of the function, means that what values of x we can substitute over here. That is the domain of this function. So we are saying that we can substitute any value of x. This function is defined for all real numbers R. It means the domain of this function, it is minus infinity to infinity, and the answer we will obtain, that is always a positive real number, or in place of positive we are not using positive real number, we are saying it is non-negative real number. That is answer can be 0 or greater than 0. Suppose we are substituting the value 2 in this, x is equal to 2, we will get y is equal to 4. If we substitute x is equal to minus 2, we will get y is equal to 4. So the value of y that we will have, that is always non-negative, that is 0 and all the numbers greater than 0. So we are saying the range of this function, it is y belongs to 0 comma infinity, and this is the closed bracket over here, because 0 is included, that if we put x is equal to 0, the answer will be y is equal to 0. Next we have is this function, it is y is equal to x cube plus 1. So we have plotted this function, these are the x and y axis, this is the graph of this function, and from the graph of this function it is clear that first thing is this function is defined for all values of x belongs to R. So the domain is x belongs to R. Next, the range is, if we substitute different values of x, we will get different values of y, and those values can be positive, these values, and these are negative values of y we are obtaining. So we are saying the range of this is y belongs to minus infinity to infinity. Next, we have plotted another polynomial function, it is y is equal to x into x minus 1 into x minus 2, and the graph of this function is of this form. Now first of all, if we have to check whether this is a function or not, so we are saying we are drawing a line parallel to y-axis over here, and we can see if we draw this line anywhere over here, it will intersect this graph only at one point, so it is a function. Next, when we have to write the domain of this function, we are saying look at this graph, it is it can take this negative values of x are possible, all positive values of x are possible. We are saying in this function we can substitute any value of x belonging to r. If we substitute any real value, we will get the answer for y. So that is why we are saying the domain of this function, it is equal to r. That is, this function is defined for all real number r. And from the graph it is clear that these values over here, the value of y is this, then the value of y is this. Similarly, this will continue like this. On the negative side, we are saying the value of y will be negative. This negative value will keep on decreasing. So what we get is that the range of this function is equal to r. That the answers we obtain for this function on substituting different values of x. So the range of this function, that is equal to r. We will see how to calculate the domain of range of these functions in detail in our next lecture, that how we can calculate the domain and range. But right now we are just restricted to these functions and their graphs. Now the next function we have, it is constant function. So we are saying if the range of the function f consists of only one number, then that function is called a constant function. So the graph, the example if I have to give, we are talking about fx is equal to 4. We are saying f is a function defined from r to r. So what this thing means, that if you substitute f of 1, answer is 4. If you substitute f of 2, answer is 4. You substitute f of 3, answer is 4. Whatever value of x you will substitute, you substitute f of pi, the answer is 4. So we are saying for any value of x, we are saying for any value of x, the value of y, it is fixed. So when you draw this function, you will get a straight line over here, and this function, it is called a constant function. It is fx is equal to c. So this function is called a constant function. We are saying domain of this function, it is r, and the range of this function, it is c. Next we have is identity function. So the definition of identity function is the function y is equal to fx equal to x. We are saying any function which is fx is equal to values fx is equal to x. Suppose f is defined from r to r. So what the value it will give? If you substitute f is equal to 1, the answer is 1. If you substitute 2, the answer is 2. If you substitute pi, the answer is pi. So you substitute any value x belonging to r, you will get the same answer. We are saying fx is equal to x. The graph of this function will be in this form. We are saying for 1, the value of y, it is 1. If you substitute x is equal to 2, the value of y, it is 2. If you substitute x is equal to minus 1, the value of x is minus 1. If you substitute x is equal to minus 2, the value of y you will get, it is minus 2. So this is the straight line we are obtaining over here. This is the graph of the function y is equal to x, that is the identity function. All these functions, these are the algebraic functions, because if we are talking about fx is equal to c, so this is also a polynomial function. If we are writing fx is equal to x, this is also a polynomial function. Now the domain of this identity function, it is r, and the range of this identity function, it is r. We are drawing these polynomial functions over here, these algebraic functions over here, and we are saying the domain and range there are. How we are getting this? We are saying what values this function can take, what values of x are possible over here. We are saying if we take any value on the x, we draw a line parallel to y-axis. First thing is it will intersect this line at some point. We are talking about this line, and a line parallel to y-axis we have drawn over here. So we are saying we can draw this line anywhere on the x-axis. So that is why the domain of this function, it is r. Second thing, we are saying this line, it intersects only at one point. So we are saying it is a function. Next thing we are saying is from this graph, it is clear that we can obtain any value of y. For any value of y, if we draw a line over here, we will get the corresponding value of x. So we are saying the range of this graph, it is also R, that is real numbers. Next we have are the rational functions. So if we are given two polynomial functions, say one function, it is px is equal to this is one polynomial, and second is a polynomial qx is equal to this polynomial. Then we are saying the rational function, it is fx, we are writing it is equal to px over qx. Now qx is there in the denominator, so we are saying that qx should not be equal to 0. This is just like the rational numbers we have defined. We are saying rational number is a number of the form p by q. Q is not equal to 0. P and q, they are integers. Similarly, we are saying rational function, it is, we have two polynomial functions px and qx. So rational functions are functions of the form px by qx, where qx is not equal to 0 and px and qx both are the polynomial functions. Now it is given that qx is not equal to 0. It means we cannot take those values of x. We are talking about the collection of those values of x for which qx is equal to 0. It means this x cannot take the values from this set. So this gives us that the domain of the function f, that is equal to all real numbers minus all those numbers x for which qx, that is equal to 0. Next we have irrational functions. So irrational functions are an algebraic function having non-integral rational exponent is called an irrational function. So we are saying the powers over here we are having, they are irrational, non-integral rational exponents. That is, these are not the integral values. So these kind of functions we are saying, these are called the irrational functions. So these are some of the examples of the algebraic functions. Next we have are the transcendental functions. So functions which are not algebraic, that is, they cannot be constructed using the algebraic operations starting from polynomials, then those functions, these are called the transcendental functions. So some examples of transcendental functions, they are exponential functions, logarithmic functions, trigonometric functions, inverse trigonometric functions. So these are the examples of some non-algebraic functions, and these are called the transcendental functions, and we will see the definitions and the graphs of these functions in our next slide. So the first function we are going to talk over here, it is the exponential function. So exponential function is the function fx is equal to a raised to the power x for any a greater than 0 and a not equal to 1 is called an exponential function. So suppose we are talking about a function fx is equal to 3 raised to the power x, or fx is equal to 2.1 raised to the power x. So all these functions we are saying, these are called the exponential functions, and the graph of these functions, these are shown over here. We are saying when the value of a lies between 0 and 1, the graph of this function is in this form. You can plot these values and you can see the answer. So why we are getting this kind of answer? Because when the value of a is between 0 and 1, suppose the value of a we have taken, it is 1 by 2, that is equal to 0.5. So we are writing the function, it is fx is equal to 0.5 raised to the power x. Now what will happen? If I substitute, suppose I substitute the value of x is equal to 1, the answer I will obtain f of 1 is equal to 0.5. If I substitute x is equal to 2, so f of 2 I will have 0.5 square. So what is happening over here? This value is 0.5, this x is equal to 1. When we have increased the value of x to 2, this value will be decreased. The answer will be 0.25. So we are saying as the value of x is increasing, the value of fx is decreasing. Now if we take the value of x is equal to -1, the answer we will get it is 0. In place of 0.5, suppose we are writing it is 1 by 2 raised to the power -1. The answer we obtain it is 2. So the value it has increased. So we are saying these are the values of x we are talking. At x is equal to 1, this value is there. Then at x is equal to 2, the value has decreased. For x is equal to -1, the value has increased. So we are saying that this function is increasing in this direction. That in this direction the function is increasing. Now if we take the value of a greater than 1, we are not talking about the case when a is equal to 1 because it is not defined for a is equal to 1. So we are saying when a is greater than 1, suppose we are writing the value of a is equal to 2. So the function we have fx is equal to 2 raised to the power x. So as we increase the value of x, the value of fx will increase. This is shown over here, that the graph of this function will be in this form. This is the graph of this function. So from this graph, it is clear that the function is defined for all values of x. The function is defined for all values of x. It is important to note over here that it is a is not equal to 1. It doesn't mean that the value of x is not equal to 1. We are saying the domain of this function it is R. That is, you can substitute any value of x that is real in this function. And what is the range of this function? Now for the range, if we look at these graphs, we are saying what are the possible values of y? The y is always positive. First thing is clear that y is always positive. It cannot be negative. Now if we talk about the value 0, suppose I am talking about this case when a is greater than 0, and I am talking about the function fx is equal to 2 raised to the power x, and I go on increasing this value of x, then we are saying the value of fx will go on increasing. Now second thing what we are going to do is, we are saying if we go on decreasing this value of x, if we put x is equal to -1 by 2, answer is somewhere over here. If we put x is equal to say -5, answer is somewhere over here. If I put x is equal to -10, answer is somewhere over here. If I put x is equal to minus say 10,000, the answer is somewhere over here. But this answer will never become 0 for any real number. We are saying for no real x, for no real number x, 2 raised to the power x will not be equal to 0. It means 0 is never the value of y. So that is why the range of this function we are saying it is 0 to infinity. That is the possible answers for this a raised to the power x. They are always positive or they are always greater than 0. And all the numbers greater than 0 we write it in the form 0 to infinity with the open brackets. Next we have is logarithmic function. So these are fx is equal to log ax. Previous function it was fx is equal to a raised to the power x, where a is not equal to 1 and we are saying a is greater than 0. Now logarithmic function, it has definition fx is equal to log to the base ax. There is a complete video related to log. You can get the detail of these functions from that video. So over here we are just talking about the graphs of these functions and the domain and range of these functions. Over there you will come to know what is basically log and what is anti-log and what are exponential functions. All these things you will come to know from that particular video that we have made related to the log and logarithmic functions or logarithm. So over here, if we look at these values, the graph of this function, it is shown over here. This is the graph of the function when a lies between 0 and 1, and this is the graph of this function when a is greater than 1. So you can just look at this function, logarithmic function, as the inverse of the exponential function. This function we are talking about, logarithmic function, you can just see this function as the inverse function of the exponential function, and you can obtain these graphs by just rotating the axis, or if we are saying by replacing the x-axis with y-axis, these graphs can be obtained over here. So in this case we are saying that the domain is the set of all positive numbers. The domain of this function, it is the set of all positive numbers, it is 0 to infinity, and the range of these numbers, it is all real numbers. This is the range of these numbers. So just for the sake of completeness of this video, I give a little bit explanation of log over here. So we are saying, suppose we have b is equal to log ax, then what this thing means is b is equal to this thing means is a raised to the power b, that is equal to x. Now if we are talking about the exponential function, it is y is equal to a raised to the power x. So if we take log, so we are getting log y is equal to x log a. Now if we take the base of this log to be a, if we take the base of this log a, so we are having log a to the base a, that is equal to 1. So what we get is that x is equal to log y to the base a. So if we are writing y is equal to a raised to the power x, this is the exponential function, we are saying this is just equivalent to writing x is equal to log to the base a y. Both these things, these are equivalent to each other. So similarly we are saying if we are writing fx is equal to this, that is equal to y, so basically we are saying it is x is equal to a raised to the power y. So if we compare this function with the exponential function, the definition of exponential function we have, it is y is equal to a raised to the power x. This thing we have done. Exponential function, we have seen the graph of this function and the domain and range. So we can see that this function x is equal to a raised to the power y, it is just the inverse of this function. So the graphs, they are obtained by replacing x-axis with the y-axis. These values of x and y, these are interchanged. So these graphs, these are just obtained by rotating the graph of exponential function by 90 degrees. The domain of the exponential function was set of real number. This was domain for exponential function. In this case, this is range of logarithmic function. Similarly, this is domain of logarithmic function, and this is range for exponential function. So both these functions, these are related to each other, and more details will be clear to you when we move on to our next slides. So these are some properties we have listed related to the logarithmic functions, and the details of these are discussed separately in the video on the logarithmic functions or logarithms. We have made a separate video on logarithms, and the details of these functions, they are explained, these properties, these are explained over there. So we just mention these properties one by one over here. First is that log to the base e a into b, that is equal to log to the base e a plus log to the base e b. So we are saying if two numbers, these are product over here, then these two numbers, these can be separated like this, and it is log a plus log b. Similarly, if it is log a by b, then we have it is log a minus log b. Next, this power is there, it is log a raised to the power m. Then this power comes here and it becomes m log a. So you can just go through these properties once, and in our next slides we will see how we are going to use these properties and how we are going to solve the problem based upon these. Now the next function we have, it is the trigonometric function. So right now, whatever the trigonometry that you have studied, that was using the triangles. We are saying we have a triangle, we have an angle theta over here, this is the perpendicular, this is base, and this is hypotenuse, and we have talked about the sine theta, cos theta, tan theta, then secant theta and cot theta. Now in this class, in class 11th, you will study about the trigonometric functions. These are basically the circular functions that we are talking about. A circle and a point on this circle is moving, and we have calculated this is the angle x we are saying, and corresponding to this angle x we have the functions over here, and the graph of these functions, these are mentioned over here. So first we have it is fx is equal to sin x. The details of these functions you will study in your chapter of trigonometric functions. So right now you can just look at the graph of these functions, how we are obtaining this graph. These will be more clear to you in your chapter of trigonometric functions. So fx is equal to sin x, it has a graph in this form. So this graph, it continues like this, it is not ending over here, it continues like this. So we are saying the domain of this function is R. In your previous classes you have studied the trigonometry, and over there this angle was restricted to the values 0 is less than theta is less than 90 degrees. But when we are talking about trigonometric functions, these are defined for all real number R, and the domain of this function, it is real line, and the range means that the maximum and minimum value that this function can have. So the maximum value it can have, it is y is equal to 1, and minimum value it can have, it is y is equal to minus 1. So the range of this function is closed interval minus 1 to 1. Next we have the function, it is cos x. The graph of this function is shown over here. Again, it is infinite on both sides. So the domain of this function means what values of x cos can take over here, it is all real numbers, and the range of this function, it is minus 1 to 1, that is the maximum and minimum values we can have over here, they are minus 1 and minus 1 respectively. Next function we are talking about, it is the tan x. Now the graph of this function is shown over here. These are the graphs of this function. Now it is clear from the graph that for these values over here, that is for minus pi by 2, pi by 2, 3 pi by 2, minus 3 pi by 2, this function is not defined. So we are saying that the domain of the function is r minus 2n plus 1 pi by 2. So what this thing basically saying is that we are saying that value of tan x we have, it is sin x over cos x, and we know that tan x, it is not defined for 90 degree. I am talking about the trigonometry that you have studied. We are saying tan x is not defined for 90 degree. So basically what we are saying is that tan x is not defined when value of cos x is equal to 0. So these are the points where cos x is equal to 0. These are the values of x for which cos x is equal to 0. So we are saying these are the points from the real line. If we remove these points, these are the points where the tan x, it is defined, and the range of tan x, what these functions are, these are infinite. These graphs we are talking about, these are infinite on both sides. The value it goes on increasing in this way. So the value of y that we can have, it can attain any value. So the range of tan x we have, it is equal to r. This is the range of the function tan x. Next we have, these are the graphs of cosecant x. Fx is equal to cosecant x, fx is equal to secant x, and fx is equal to cot x. And cosecant x, we know this is equal to 1 over sin x. Secant x, we know it is 1 over cos x, and cot x, we know it is cos x over sin x. So this cosecant x will be defined for all values of x except for which sin x is not equal to 0. Secant x is defined for all values for which cos x is not equal to 0. And sin x is defined for all values of x for which sin x is not equal to 0. And these are the graphs of these functions. That if we plot these functions on the x-axis and y-axis, we will obtain the graphs in this form. And from this graph also it is clear that this function is not defined for these values over here. That if we are talking about secant x, it is not defined for 0. It is not defined for 3 pi by 2 comma this point we are saying it is 3 pi by 2, or it is minus pi by 2. It is not defined for all these values. So the domain is basically the set of all real numbers except for those numbers for which sin x is equal to 0. If we look at the range of these numbers, we are saying range is real numbers minus the interval, this, the values, this function, it does not take the value from this portion. So we are saying we have removed this portion from the real numbers. Similarly, for secant x, we are saying the range is, we have removed this portion from the set of real numbers. So it can attain all the values except for the numbers within this range. Similarly, for cot x, we are saying we can obtain this function from the tan x also. So it is not defined for minus pi, 2 pi, all these values we are talking about, it is 0. This function is not defined for these values. These are basically the points where sin x is equal to 0. And again, these graphs we are saying these are infinite from both sides. So the range of this function cot x we have, it is r, that is the values it can attain, that it is real numbers, that it can attain any real value.